All right, so we're going to start chapter one, which is limits and their properties. And this first section is really just a preview of calculus. So we're going to get into limits a little bit, but it's really more of an idea of what is calculus and how we're going to use it. So the objectives are we're going to start to understand what calculus is and how it compares with pre-calc. Understand that the tangent line problem is basic to calculus and that the area problem is also basic to calculus. And then there's also an AP video for the notes that's linked, and that is on your AP classroom that we joined earlier. So that would be something probably worth watching as well. So the first part, what's calculus? So just kind of reading through this for you. Remember that when we do pre-calculus, the pre-calculus math is more static, whereas calculus is more dynamic. And really what that means is that the static is that it's just kind of stuck, or we're looking at something that's not really moving, where calculus is a lot more about the movement and how things are changing. So some examples would be that an object traveling at a constant velocity could be analyzed with pre-calc. And then to analyze the velocity of an accelerating object, you need calculus. So, in pre-calc, we would say, okay, the velocity is constant, so we don't have to worry about the velocity or the speed of the object changing. Where in calculus, we're going to be able to analyze an object with a changing velocity or a changing speed. The slope of a line can be analyzed with pre-calc, but to analyze the slope of a curve, you need calculus. So we're going to be looking at the slopes of curves at points, so at instantaneous points, which would really be your tangent line. The curvature of a circle is constant and can be analyzed with pre-calc, but to analyze the variable curvature of a general curve, you would need calculus. So again, it just takes away that really specific piece and allows you to go more broad with it. So just that idea that the pre-calc is more static, where calc is more dynamic. So one way to answer the question of what's calculus is to say that calculus is a limit machine that involves three stages. So the first stage is pre-calculus math, where you have slope of a line or area of a rectangle. The second stage is the limit process, and then the third stage is a new calculus formation, such as the derivative or integral. So these are kind of the three stages. So you're good with the pre-calc math. We're going to get into the limit process in this chapter, and then we're going to move into the actual calculus in the next chapter. So it's a process where it's not just memorizing formulas. You actually have to understand the process. It's like learning a new language. And so understanding kind of that base of the language and then building from your base. So these are just some visuals that we kind of already talked about, where if you wanted to find the slope of a line without calculus, you would have to find the slope, the change in y over change in x between 2 points. Where if we had this point right here and we wanted to find the slope of this tangent line, we would have to use calculus and look at the derivative of y with respect to x. The secant line to a curve, again, the secant line is a line between 2 points, versus we could actually do a tangent line where we only have 1 point. So we'll be able to find equations for tangent lines at a specific point. Without calculus, we could find the average rate of change, but with calculus, we can find the instantaneous rate of change. And then we could find the curvature of a circle without calculus, and we could find the curvature of an actual curve, so something that's not so formulated like a circle. And then just more examples: height of a curve versus maximum height, tangent to a sphere versus tangent just to a surface, and then the direction of motion along a line versus a curve. So when we're getting into area, without calc, we can do the area of a rectangle. With calculus, we'll be able to find the area of more irregular shapes that are under curves. We could do work with a constant force. With calculus, you could have work with a variable force, so that's more of a physics concept. Without calc, we could do center of a rectangle. And with calc, we could actually find that centroid of a region. And then without calc, the length of a segment. And then with calculus, the length of an arc. So again, that curved line. When we're dealing with volume, you have surface area of a cylinder versus surface area of, a shape that is not a regular shape. You could do mass of a solid of constant density versus mass of a solid with a variable density, volume of a regular solid, volume of a region under a curve. So again, something that's not regular. And then the sum of finite numbers versus the sum of an infinite number of terms. All right, so the tangent line problem is the notion of limit is really fundamental in terms of calculus. So the following descriptions of two classic problems. We have the tangent line problem, and then we'll get into the area problem. And this is really kind of the two very general ways that calculus is used. So in the tangent line problem, you're given a function f. So if you notice, that's this curve right here. So you're given this function f, gives you this curve. You don't maybe necessarily know what that is. And a point P, so that's that point P right here. And you're asked to find the equation of a tangent line to the graph. So you're asked to find the equation of this tangent line that's tangent to that point. So tangent means it just touches the point one time. We don't need the 2 points. So except for cases involving a vertical tangent, because with a vertical tangent, you would have an undefined slope, and so you wouldn't actually be able to do the problem. But the problem for finding a tangent line is equivalent to finding the slope of the line at P. So you could start by approximating. Again, if this is your point P right here, then you could pick another point somewhere down the line right here, we'll say. And so what we did, so if this point P had the point C and f of C, then this point up here would be C plus whatever that change in x was, and then f of C plus that change in x, right? And so really this point has that as its y coordinate. And so if you want to define the slope, then you would do your y2 minus y1 over x2 minus x1. And that's what this part is right here. So this is like your y2 minus y1 over your x2 minus x1. And if you simplify that, you get that f of c plus delta x minus f of c over delta x, which maybe looks a little bit similar to you from our last chapter. So what happens is as that point that you picked, as that point moves closer and closer to P, you get a more accurate representation of what the slope of that tangent line is. So that idea of when your limiting position exists, the slope of the tangent line is said to be the limit of the slopes of the secant line. So as you get closer and closer, if you were to keep getting closer and closer, when you're infinitely close to that point P, and so you're really still finding the slope between P and some other point that's infinitely close to it, that would be the slope of your tangent line. So then when we look at the area problem, just as a kind of a simple example, if we look at this f of x, and then we have the region bound by the graph, the f of x, and then the vertical lines x equals a and x equals b. Right, so we're trying to think about what is that shaded region, that area of that pink part of the graph. So you can approximate it with rectangles. So what you would probably do is split into a certain number of rectangles that have an equal base. And the more rectangles that you have underneath your curve, the more accurate the area of the curve is going to be. So that's what this says right here. As you increase the number of rectangles, the approximation tends to be better and better because the amount of area missed by the rectangles decreases. And so your goal would be to determine the sum of all the areas. So you would actually go through and calculate the area of all the rectangles and add those together.